All right. Well, welcome everyone to There is no such thing as a free thermodynamic lunch. Real course, before we get started, a huge thanks to one of our top tier sponsors, April Air. You're looking at humidity control, temperature control, and air purity. Water efficient humidification is a win for health and water conservation. Energy efficient dehumidification pairs with right size heat pumps to keep air feeling cool and have a higher set point to reduce energy. MERV 13 filtration captures particulates of growing concern, especially airborne viruses, PM 2.5, wildfire smoke, VOCs, dust, and more. So April Air has many different ways to keep you healthy, and radon is increasingly becoming a problem. It's the second cause of lung cancer after smoking. We've been testing many homes with high radon issues, even in non-designated EPA radon zones. So we highly encourage you to get tested and get a system installed. And April Air has some systems for you to check out if you want to be safer. So go to aprilair.com for radon and other healthy home aspects today. And also thanks to our second tier sponsor, Aware, you might want to get a sense of what the air quality is in your house. And so you can track that now through temperature, humidity, CO2, TVOCs, and PM 2.5 right in real time. They have a movable unit and one that can be integrated right into the house, similar to how you would integrate a smoke or CO2 detector. We can imagine air quality monitors being displayed throughout the house. So check them out over at aware.com. All right, we're going to get started here shortly on our webinar, but before we do, a real quick introduction. We are the Green Home Institute, a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation and construction of the places we live. Today, I will be your moderator. I am the education director here, Brett Little at GHI, and we have a very small team. Our new program manager, Eliza, and our executive director, Jose Reyna, all here to help assist you. As with always, our course is approved for multiple continuing education units, as well as the Passive House Institute US, AIA Health, Welfare, and Safety, which may make it applicable to your state-based design or contractor license, as well as our Certified Green Home Professional designation under Energy, Health, and the Materials pillar. All right, so with that, I am super excited to introduce our speaker here today and hand it off to him. Joe, I'm glad to have you on. I think a lot of people know who you are, but feel free to take it away, introduce yourself to those who don't know, and glad to have you. Welcome.
Well, thank you. It's always an honor and a pleasure to talk to people based in Michigan. I learned about Werner's and Buddy's Pizza, and I would drive down from Toronto to buy ski equipment. So I have a lot of warm relationships with Michigan. Of course, now I'm an American and having a blast living in Boston, so all is well. I investigate building failures. I have 3 engineering degrees. I used to be a builder, and I never get a call saying, "Joe, things are going great. Let's have a beer." I don't get that call. I get the call, it's the end of the world. The vampires have come, and you got to help us. And so I basically say that failure has made me the man that I am today. So the idea is that you can learn a lot from a failure if you then take the lessons of the failure and change the way that you build, design, and operate to get a much higher performing building. And so all of the lessons that I've learned and I'm going to be sharing with you come from serious mistakes that we've done over the past century. And so the idea is that maybe we should be smarter about things and not get into as much trouble. So with that, I'd like to start with my session. There's no such thing as a free thermodynamic lunch. Energy flow. We're insanely dealing with energy efficiency. There's no such thing as a free thermodynamic lunch, and what that really, it comes from something called the second law of thermodynamics, which we will talk about later, but it was put to music by the second best guitarist of all time, Mark Knopfler, and you can't get your money for nothing and your chicks for free. That's basically the second law of thermodynamics. And how it relates to us is that the energy flow across a building enclosure has been dramatically changed. We've significantly reduced the energy exchange. And most people don't understand that there are consequences for that. So this is a project in Cleveland in the early 1980s, and thousands of houses started to have peeling paint problems. And they'd never had peeling paint problems before, but all of a sudden they had peeling paint problems. And I got involved for stories that I can't really tell you about, but there I am when I was a youngster. And it turned out that when people insulated their walls, retrofitted their walls with cellulose insulation, the paint fell off. And they're like, huh, what? Well, what happened is that the cellulose insulation did its job. It reduced the energy flow. Well, how did the wall get wetter? Well, the wall never got wetter. The wall was always getting wet. But because the walls were energy pigs, the energy flow dried the assembly out. So what was happening is that water has always been getting into the laps of siding because of capillarity. And when you have an energy exchange, this moisture evaporates, it dries. So as we reduce the energy flow, the dwell time for moisture in the assembly went up. Wetting that's followed by drying, relax, take a Valium. We don't have an issue with that. But wetting that's not followed by drying leads to issues. Now, back in the day, when my Toronto Maple Leafs were winning Stanley Cups, that would be in the 1960s, by the way, we would call this incidental water. Because, so what? We build outside, things get wet, it dries, relax. Well, the trouble now is that incidental water is no longer incidental, and we have to manage the water today in new buildings very, very differently than we did in old buildings. Now, the new buildings are easy because we can start with a clean sheet of paper. The issue is, oh my God, what do I do with the retrofit? I just can't replace the windows. I just can't do this. I have to do this, this, and this, and this. Well, why? Well, because you've dramatically altered the energy exchange. This is a project that brings back a lot of fond memories. I lived across the street, and what happened was that the neighbors insulated the attic, and all of a sudden, we had all kinds of condensation and corrosion and decay in the attic. So we never had this problem before. Well, we vented the attic. Yeah, I know we vented the attic, but let me explain. Attic ventilation only removes moisture in poorly insulated attics. Huh? Well, if I've got cold air outside in the winter, and what are the odds that you have cold air outside in the winter? Well, cold air can't hold moisture, can't pick up moisture. So you bring cold air that doesn't have much moisture in it, and you bring it into a poorly insulated attic. Well, the heat loss from the house warms up that cold air, and if there's any moisture present, moisture's picked up and it's carried to the outside. Well, where did the moisture come from? Well, it came from the inside because of air leakage. So the attic ventilation ratios that came to us from the 50s and 60s are based on poorly insulated attics. Well, what happens when we have a super insulated attic? Well, we don't have any energy flow. And so what happens is I'm bringing in air that's dry in an absolute sense, but at a very high relative humidity. There's not very much moisture in the air, but it's very close to the maximum amount it can hold, and it has a high relative humidity. Well, hygroscopic materials see relative humidity. They don't see the absolute moisture, they just see the relative humidity. Nobody knows why. You figure that out, you'll get a first-class ticket to Stockholm to get your Nobel Prize in physics. So ventilating super insulated roofs with high relative humidity air that's dry causes them to get moldy. So it's insane. We can't do things the way we used to when we change the energy flow. And what happened was that the first solution to this was, well, let's make the ceilings airtight, keep that moisture from getting into the house, into the attic. Of course, that changed the ability of the combustion appliances to work, and we find it we're beginning to kill people. It's not a good thing to kill somebody in order to save some energy. And so then we got into sealed combustion. We had to deal with makeup air. And the whole point is that there's no such thing as a free thermodynamic lunch. A house is an interrelated system. A building is an interrelated system. And we have to know how the interactions work. It's not just in cold climates. I mean, this is this is the deep South. They all talk funny. And let's put radiant barriers. Well, they actually work. They make the attics colder. Well, if the attic is colder, we've got ductwork in the attic. The ductwork is filled with cold air, and the ductwork is insulated to R8 only. Well, the surface of the ductwork is going to get cold and it sweats. So one of the biggest problems with radiant barriers is it causes the ductwork to sweat. And when it sweats, it drips down and people get really freaking irritated. Well, where's the moisture coming from? Well, it's coming from outside air that's brought in because we ventilate attics in the South. And I'm telling you, that's a really dumb idea. Why would you want to ventilate an attic with hot, humid air? You would want to ventilate it with dry air. Well, where are you going to find dry air south of the Mason-Dixon line and east of Interstate 35 in Texas? It's just so we figured out that look, we either move the attic, the ductwork inside, or we move the thermal boundary up, or we don't vent. Now, when we started not venting attics, we found that they didn't blow off in hurricanes. Unvented attics don't blow away. Vented attics do. It's amazing. It's just beginning to catch on. It only took 20 years, but it's catching on. Also, unvented attics don't burn as much as vented attics. We have wildfire. We lost, 1,000 houses outside of Boulder last year, or a year and a half ago. And most of the stuff happened because of the embers being carried into vented attics. So you're telling me that I shouldn't vent my attic because it doesn't blow away in a hurricane and it's a lot safer from a wildfire perspective. Well, there's got to be a catch. Well, of course there's a catch. There's always a freaking catch. Do you have snow in Michigan? Yeah, we have snow where I grew up. And so, do you know what the R value of snow is? Around R2 per inch. I know this because I grew up in an igloo. I was born in Canada, remember? So if I have 10 inches of snow on my roof, I got a thermal resistance of R20, which warms up the temperature of the roof snow interface, and I'll get an ice dam. And so I have to ventilate heat from the underside of the deck to control ice damming. Well, can I go to R60 or R70 or R80? And the answer is, no, it don't work. Well, how do I do the wildfire thing in a high snow load area? Well, I build an unvented roof, and then I build a vented over roof with basically fire dampers. So in high snow load areas, I will close the vented part to handle ice damming when a fire approaches. Well, that's going to add cost. Well, it's a lot less expensive than paying for a new building. Well, nobody does this. Well, they are now. Well, why? Things are burning down. Yay, fire, woohoo. All right, it gets even better. So let's go back to the South, just for, a hoot. I go from R19, R20 insulation in attics in Florida and in Texas and I go to, now we're talking about R40, the code's calling for R40, R39. Well, what happens to the temperature of a ceiling in a closet that's touching the insulated drywall? Look, it's really cold because there's no load in the closet. And as it gets colder, the relative humidity on the surface goes up and we get mold in closets. So when we increase the insulation level in the attics, we got moldy closets. Of course, the answer is, well, just put in a louver door. Well, of course, people don't like louver doors. Well, put in a transfer grill. Oh, I don't like that. So I wanted to get a code change to have return air pulled out of the closet, and the code people's heads exploded, and that didn't pass. But I got a provision in Florida saying I can put in a closet ventilation system as long as I don't connect it to the air conditioning system. Code people, yeah, whatever. So where are we going with this particular house? It's a cold place. It's Maine. It's gorgeous. It's old. It was perfectly happy. Perfectly happy. Vented. Crawl space, vented for a long freaking time. No issues at all. And then all of a sudden, on plastic ground cover, people notice, oh my God, there's water on the top of the plastic. Well, never happened before. Well, what's going on? Well, they had insulated the floor. Well, what that meant was that the crawl space became colder. We weren't getting heat from the house. As things got colder, the ventilated air that was coming in from the outside was condensing on the plastic sheet and the underside of the floor. So you're telling me an ventilated, uninsulated attic is durable, but a ventilated, insulated attic is a problem? Yeah, unless you do it very differently. And what happened was this happened in Maine first, and the technology was exported to Tennessee. So we had the Tennessee Valley Authority start a program to insulate crawl spaces throughout their service area, and the living room furniture began to meet the crawl spaces. So what are you saying, Joe? You're saying that it's a dumb idea to ventilate your crawl space? We've been doing it a long time. Well, yeah, we did it with real wood, and we didn't do it with insulation. What do you mean real wood? Well, okay, I view engineered wood as an insult to wood and engineers. I call OSB the spam of wood. I call spam the OSB of luncheon meats. And I remind people that, youngsters especially, we used to go to forests and cut trees down and cut them into boards and build boats out of them and sail them around the world. I tried doing that with a sheet of OSB. Well, we're going to go back to building out 1,000-year-old trees, and no, we're going to be dealing with more moisture-sensitive materials, so we're going to have to change the energy balance and the wetting and drying. So the risk of crawl spaces have gone dramatically up when we go to I-joists and OSB and insulate them. And I'm saying, well, you should build them like mini basements. In other words, you insulate the perimeter and you make the crawl space part of your house, not to the outside. Well, what if I'm in a flood area and I don't want to? Well, okay, then you have to put rigid insulation on the underside of your floor. That's a vapor barrier, so that you're completely disconnecting your crawl space from the house. So you've got two approaches. You either connect the crawl space entirely to the house or completely disconnect the crawl space from your house. It's when you're in the middle that you get into trouble. So in a high flood zone, disconnect it from your house. Everywhere else, connected to your house. Well, the Pink Towers, where is this? Of course, this is Orlando. I mean, I couldn't resist. This was really neat because they discovered mold. And, well, why? Well, they air condition. I know you're shocked at this. They air condition. So when the inside is colder than the outside, moisture goes from the outside to the inside. And let's put a vapor barrier on the inside, vinyl wall covering. And so we would end up with air-conditioned buildings with vapor barriers on the inside and hot, humid, and mixed humid climates, and there was a freaking disaster. And the people that pioneered this were the hotel industry. And you would get, pink spots on the vinyl, yellow spots, and we called it the Marriott measles, the Radisson rash, the Hyatt hives. Well, I'm not air conditioning, I'm not vinyl. Yeah, but we began to put plastic vapor barriers on the inside of our walls. Well, we actually do this in cold places like Michigan. Yeah, and do you air condition? Yeah, sometimes. And do you have a lot of insulation? Yeah. Maybe it's a dumb idea to put a vapor barrier on the inside of a wall, even in a cold climate. How do you know that? Well, I grew up in a colder place, and it was a dumb idea. Well, Canada exported, plastic vapor barriers to the United States. Well, why? Well, to get even for the Wayne Gretzky trade. You get our best hockey player, we're going to rot out your house. This was, part of what's called quid pro quo. So you should not have a plastic vapor barrier in any building that's air conditioned, even in a cold climate. And look at this. All right, a little bit of physics. Rainscreen equation. It's the third most famous equation in physics, and which of course why nobody knows about it. Svante Arrhenius won the Nobel Prize for Physics in 1912, 1913, but it was a huge scandal because he was a chemist. Nothing irritates the physics community than having a chemist come in and kick physics butt. It's like having a holistic medicine person beat up a brain surgeon. It's fun to watch. But so here's the equation, and it's sort of like breathtaking, isn't it? It's called an engineering joke. There's no numbers in this, all right? Everybody relax. But what it basically says, because you got those letters above the big letters, you got these, it's an exponent, it's a whoosh. In other words, it's a exponential relationship. It's not linear, it's not a whir. Whir, linear, whir, okay, exponential, whoosh, whoosh, bad. So let me translate. So for every 10 degree Kelvin rise, reaction rate doubles. So let's make this useful. 10 degrees Kelvin is 10 degrees Celsius, which is 18 degrees Fahrenheit. Using geomath, which is a field of math I invented, that's around 20 degrees. For every 20 degree Fahrenheit increase in temperature, you double badness. Huh? Things go bad the hotter they are. And it's not a whir, it's a whoosh. It's a whoosh. So if I have a black EPDM membrane in the middle of July, 2 o'clock in the afternoon, it's 180 degrees Fahrenheit. And I replace that black membrane with a white TPO membrane, it's going to be at 120 degrees. Oh my God, which membrane is going to last longer? The white membrane, because it's colder. But which roof lasts longer? The black one. Huh? It has a higher drying potential. It has way more energy. When we changed the color of our roofs from black to white, you had to add air barriers and vapor barriers, and it had to be incredible good workmanship because you can't get your money for nothing and your chicks for free. There's no such thing as a free thermodynamic lunch. And the Uranus equation says that. Now, it runs what we call the three principal damage functions. There are about a dozen of them, and damage functions mean that, I cause damage. So water is the worst of the worst of the worstest, followed by heat and ultraviolet light. And each one of these are exponential. They're whooshes. They're not linear. But it's worse. They're synergistic, which means they're not additive, they're multiplicative. So the effect of water by itself and the effect of heat by itself, if you add the two together simultaneously, you're not adding them, you're multiplying them. So the part of the building that sees water, heat, and ultraviolet light simultaneously, you're going to have a bad day. Well, what part of the building sees the most water, heat, and ultraviolet light? Well, the roof. Where the building touches the sky is the biggest stress, followed by where the building touches the ground, followed by the sides. So what's neat about this is things go really bad with roofs really quickly. And an observation is stupid should hurt. And you can say, huh? Well, when you're a kid and you put your hand on the stove, ow, it hurts, you learn right away. If you were to put your hand on the stove and not be hurt for 10 or 20 years, you haven't learned. So we had to learn with roofs because the damage functions acted so quickly, we reacted quickly. The problem with the walls and the rest of the building is that it took maybe 15 to 20 years before the stupid action resulted in a consequence. And what's been happening is the latency period, the time period for the action, the design or the construction, and the damage is shrinking. It's getting narrower. So instead of a 10-year gap, it's now 3 to 5 years. Now, why is that important? Well, we're learning mistakes much more rapidly, and the people that are responsible end up having to be, you can't run and hide, right? So there's good and there's bad. The good part is that it's happening fast, so we learn quickly. The bad part is that it's happening. Yeah. All right. Second law of thermodynamics. There are there are 4 laws of thermodynamics, but we only number them up to 3 because we forgot one. So we had the first, the second, and the third, and then somebody said we need another one, and we couldn't call it the fourth because it was too important. We couldn't put it between the second and the third and the first and the second because all the textbook would change, so we called it the zeroth. So the zeroth is if A equals B and B equals C, A equals C. I didn't think they needed a law for that. I mean, I thought didn't some dead Greek come down from a mountain with, I think I'm getting the stories mixed up, but apparently the Germans didn't understand the Greeks. It was all Greek to them, and so they came up with the zeroth law. The first law is basically equilibrium, something that economists don't understand with the deficit. And the third one says that everything goes to absolute zero about 1 trillion years from now, which is pretty much when we're going to balance the budget, but that's another story. The second law is the one that is the most important to builders, architects, engineers, and contractors, which is why it's never taught. See, it's really important. Don't tell anybody. So here it is. This is my translation of the second law. Heat flow is from warm to cold because. See, if there's no way of explaining it with first principles, you make it a law. It just simply says heat flows from warm to cold. You say, well, it's been proven. No, you don't prove science. You can only disprove science. See, nobody has disproved that heat flow is from warm to cold. If we got it to go from cold to warm, Nobel Prize. Anybody who says the science is settled or the science is proven is a journalist, not an engineer or scientist. Moisture flows from warm to cold. Why? Because. Moisture flows from more to less. Why? Because. You could do this experiment at home. Getting something wet, touch something dry, the dry thing becomes wet. Who knew? Dead German, wrote it in a book. Air flows from a higher pressure to a lower, and gravity acts down. This is a big deal. After you handle fire and structure, this should run your life. You see, fire and structure kills you real fast. You don't want to die. Don't kill people. Don't have it burn. Don't blow away, fall down. Then you deal with this. This is after the other stuff, all right? Now, moisture has 2 rules, warm to cold and more to less. Now, because I'm explaining it this way, everybody understands. That can't be allowed in higher education and professions. We can't use something this simple. So we call it a thermal gradient and thermal diffusion, concentration gradient, molecular diffusion. Well, even that is reasonably, if you know a little bit, okay, So we don't even use that. So we call it vapor diffusion. All vapor diffusion is warm to cold and more to less. We don't let civilians know this because, my God, we wouldn't be able to hire experts. And we still make it more complicated. We say it runs according to the thermodynamic potential. And here is the thermodynamic potential. The psychopathic chart. When it's colored, it's the psychometric chart, or the psychedelic chart. All this is warm to cold and more to less. Luke, turn off the psychometric chart. The water ends up on the cold spot most of the time. Really? Really? 18, 20 times out of 20, water going from warm to cold and more to less are in the same direction. Rarely do they act in opposite directions. When they act in opposite directions, more to less wins. Rock beats scissors, paper beats rock, more to less beats warm to cold, but most of the time it's in the same direction. So we use warm to cold as a surrogate for everything. Because most normal people can look at a set of drawings and say, this is going to be cold, that's going to be warm. They can walk into a building and say, this is cold, that's going to be warm. Very few people can go into a building and feel vapor pressure. And those that can also see dead people. So I don't think you want to. Anyway, most of the time it ends up on the cold spot. So what do? Make the cold spot warm or keep the stuff from getting to the cold spot? Really? Yeah, that's an entire graduate course in thermodynamics right there. It ends up on the cold spot, so make the cold spot warm or keep the stuff from getting to the cold spot. Huh? Really? Yeah. All right, climate. This is my contribution to building physics and building science. It's a hydrothermal model or a map of climate zones. So I came up with this. ASHRAE stole it from me, and LEED stole it from them, and so did the GSA. And so everybody ripped me off. And you should ask, well, Joe, where'd you get it? I stole it. I stole it from a dead Russian, Köppen. I mean, if you're going to steal stuff from a Russian, it's helpful if it's the dead Russian. So Köppen climate maps. In other words, a map of the plant kingdom I translated into hydrothermal regions, because I figured that the plant kingdom was a better judge of heat flow, airflow, water vapor flow, rain, wind than engineers and architects. You're telling me you based everything on the Köppen climates? Yeah, isn't that cool? Gets even better. ICC stole this and turned it into the climate zones. So this is really a map of plants. Huh? Well, somebody must have studied this. Well, yeah, me. I pulled it out of my butt, said, here we go. And so why am I saying that? It wasn't any real, I mean, I think I'm a smart, clever guy, but you don't make national decisions because, some kid pulls some idea out of his butt. That's ridiculous. Now think of the implications. There are places where on one side of the street it's climate zone 5, and the other side of the street is climate zone 4, and the code is different. What? Really? It's insane. There should have been sort of a general idea. Luke, turn off the guidance system. Go with the force. Engineers, architects, throw this away. Go with your judgment. I mean, and let's say you're in the middle of climate zone 4, and you're on the water, and 100 yards away on the hill, you have another site. Do you really think that those are the same loads? Really? Anyway, so there you go. I then created another map, a map of rainfall, and I picked 20 inches, 0 to 20, 20 to 40, 40 to 60, over 60. Why did I pick 20? Well, when I had 10, it was too complicated, and when it was 30, it wasn't complicated enough. Are you telling me you picked the map because you felt it looked good? Yeah. Well, who did this map? Well, we defined it in the code. Dry is less than 20 inches of rain. Moist and humid is greater than that. So you basically take the plant kingdom and the rainfall, and you get this. And it was just to give you a rough freaking idea. And we got lost in the stupidity and the complications. You need to use your judgment. Okay, does a building get wet uniformly? Well, no, it gets wet where it touches the sky and the edges and at the bottom. Well, that's probably the greatest risk, right? So we should probably do better things where it gets the wettest. And then what do? Then we put freaking holes. And there are only two kinds of windows in the world: windows that leak and windows that will leak. So what do we know about windows? They leak. Huh? It gets worse. Windows are like people. As windows and people get old, we leak. You youngsters have no freaking idea. Now, they've always leaked. But when we had high drying potential and we had 1,000-year-old trees and rocks, it didn't matter. Now we have to flash every punched opening and be anally fastidious about it because we don't have available energy to dry and we have more moisture sensitive materials, really. So notice how, the windows leak at the corners. So they don't leak in the middle. So we call it mustaching. And when you have a mold window, it's called a Van Dyke. These are called engineering grandfather jokes. Okay, all right. So I said, okay, come on, Joe, give us an answer. And so I came up with the perfect wall, except it wasn't my idea. I mean, I stole a 1950s black and white and I added color to it and gave it a clever name. I colorized an old drawing. I'm the Ted Turner of building science. So I gave it a name, but I took an idea from the 1950s. It wasn't my idea. I just said, look, let's take some of the important stuff and make it simple for people to understand. And I said, after you've handled the fire in the structure, you need a water control layer. Duh. And guess what? You also need an air control layer. But the water control layer is way more important than the air control layer. It's not even close. What do you mean? Well, I've been doing this for a half century now, and I've never gotten a call at 2 a.m. saying, my building is leaking air. So water control, way more important than air control. I have a lot of fun with ABBA, the Air Barrier Association of America. First of all, why would you name yourself after a bad Swedish musical group? But I said, you ought to call yourself WABA. You should have been the Water Association of America before the air. And if you look at your air barriers, basically they're water control layers that have an air control function added to them. Anyway, water control way more important than air control, and both are insanely more important than vapor control. You're better off not having a vapor barrier than having one in the wrong place. Let me repeat. You're better off not having one than having one in the wrong place. Now, having one in the right place is better than not having one, but you need to know stuff. Now, the least important is the thermal control. But it's the only one that we can actually measure and calculate reasonably well. So the code obsesses over it. U value this, R value that. All these computer simulations and how do they handle water control? Be good and good luck. That's insane. So here's what it looks like. Remember, I added color to something in black and white in the 50s. The heavy black line is the water control, the air control, and the vapor control. And it's on the outside of the structure. You want your control layer to be on the outside of the structure. The blue layer is the thermal control layer. And the reason that it's blue is Dow paid me to make it blue. When it comes in the pink range, it's going to be Owens Corning. When it's in the ugly orange, it's Rockwell. See that? You can tell who I've been consulting to based on the color of the insulation. Then outboard of that is the cladding. And all you want to have is you want to back ventilate and drain your cladding. Now, how much you back ventilate and how much you drain, it doesn't matter. You just need a little bit. Well, the building code calls for 1 inch residentially. Well, where does that come from? That was based on the mason's knuckles, fingers, and knuckles and fingers. The mason's hand was where the 1 inch came from. If attorneys laid brick, it would have been 3/8 of an inch. In commercial construction, it's 2 inches. Why? Well, because we needed to have a 2x4 to pull the mortar droppings out, and the 2x4 was 1.5 inches. And so you're telling me that this was simply based on constructability and somebody guessing at the time? Yes. Well, who's done measurements? Well, lots of people. If you have a continuous 32nd of an inch, it drains. You mean I could take a bumpy building paper and control hydrostatic? Yeah, woo-hoo! I wasn't smart enough to patent that, because if I was, I wouldn't be doing this presentation today. I'd be hung over. Now, if I take the perfect wall and I lay it down, I get the perfect roof, and I flip it the other way, it's the perfect slab. So what this means is that the physics of walls, roofs, and foundations are the same. So this is the optimal perfect roof, where you've got your control layers under the ballast. Why? And under the insulation. Why? Because I'm protecting them from water, heat, and ultraviolet light. If I replace the ballast with dirt, grass, and a goat, I get a lead point, right? So you get a green roof. The green roof doesn't work any better than this. It's just that you feel better about yourself. Dirt is not insulation, it's just dirt. If it was insulation, you'd buy it at Home Depot in bags in the insulation aisle, right? Give me a break. Well, we want to store the water up on the roof. Are you nuts? The only reason that you want to store the water up on your roof is because the town planners didn't invest in civil engineering infrastructure to be able to handle the runoff of buildings. So let's put the water on the roof. You guys are, yeah. Anyway, so do I love green roofs? Actually, yes, if they make the building look pretty. Really? Yeah, I'm tired of ugly black boxes that are energy efficient. I want it to be beautiful. I'm willing to give up some BTUs for beauty. Now, when have you ever heard an engineer say things need to be beautiful? Well, here's my logic. You might have to reach this a little bit, but I want buildings to last a long time. In order for buildings to last a long time, people have to take care of them. And in order for people to take care of things, the people have to want to take care of things. People don't take care of ugly things. Ugliness is not sustainable. Build me a beautiful building that I'll take care of, and now I have to make it ultra efficient and comfortable and everything else. But stop doing these ugly boxes. Stop that. Make it look good. All right. I flip it, I've got the perfect slab. I got dirt, stones as a capillary break, my extruded polystyrene, my plastic 6 mil poly, 10 mil poly, vapor control layer, and my concrete. Whoa! Easy. So here's where it gets interesting. I need to now put the pieces together. So put in the perfect wall, the perfect roof, the perfect slab. What's next? I got to connect them. And how I connect them is the secret of building science after the fire in the structure, right? After the fire in the structure. The people who forgot this were the Brits, and 80 people died in Grenfell, but we might not get into that. So what I want is I want to connect the wall to the roof and the wall to the foundation where I have continuity of the control layers. I want the water control of the roof connected to the water control of the wall to the water control of the foundation. The air control of the roof to the air control of the wall to the air, vapor, 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 thermal, thermal, thermal next. That's it. Yeah. Well, why do we even pay you to do design reviews? We don't teach this. Then we put a hole in it. It's called a windows. And what do we know about windows? They leak. So we want to connect the window, the backside of the window, to the control layer. So when the window inevitably leaks, the water's kicked to the outside, right? A leak is not a leak if the client doesn't see it. So how do you install windows? Connect the water control of the window to the water control of the wall, the air control of the window to the air control of the wall, thermal control of the window to the thermal, put it in plumb, level, and square, and make sure the wind doesn't blow it and suck it in. That's it. Yes, I've summarized a 300-page AMA document by simply saying continuity of the control layers. Now, the trouble is we don't have the perfect roof. We typically have sort of a hybrid. So we've got two control layers. We've got the water control layer membrane on the top, and then we've got another air and water and vapor control layer underneath. And so this is not as good as the other, but it's pretty darn good. And why is it not as good? Well, you have to replace the membrane on the top, right? Because it's exposed to the damage functions. Every 25 years, you're going to have to put on a new membrane. Well, that's okay. I can get at it. Well, yeah, but if you did it with the inverted roof, you could go 100 years. And I could get it to last 100 years? Yeah, or 20 years and maintain it every 20 years, right? Well, gee, I want to be greeny, weeny, and sustainable. Okay, well, what's the useful service life, folks? So this is the typical that you're going to get in most commercial buildings. you're going to have the water control area of the roof is going to go over the top of the parapet, and it has to basically overlap the water control on the wall. In low rise, we just overlap it. In high rise, we have to connect them because we don't want the wind to blow air up into the parapet. That construction of the parapet is incredibly complicated. We call it parapetitis because we have to connect the air, water, vapor, thermal across the structure. And who do we irritate? The structural engineer. Yeah, I know. Well, what if I have an attic? Well, okay, that works. But it blows off. And when I vent it, I have problems with it. And it has a fire. And I want to live up there. This is crazy. Well, we used to do this all the time. Now we're not going to anymore. So we can do this. And what's nice about this is in a high snow load area. In a low snow load area, I don't need the vented over roof. And so, wow, this is incredibly thermally efficient, structural, safe, tastes great, less filling. Awesome. It's expensive. I got to, whatever. And I said, all right, so you could use other materials. All right, so let's look at some of these walls. This is the classic. This is called the institutional wall, or the 500-year wall, because it will last 500 years, and it took 500 years to develop. So I've got the structure, and I've got the heavy black line. The structure is made out of rocks, because rocks don't burn. And everywhere except Turkey, they don't fall down, because we've learned how to build structurally reinforced masonry buildings, but it's not going to go there. On the inside, I've got sheetrock, because rocks don't burn. On the outside cladding, I've got rocks don't burn. And in between the cladding that doesn't burn and the structure that doesn't burn, we can have compressed napalm, which I understand is a Dow product. In other words, the risk here is very, very low. But could I make it out of fluffy rock? Well, sure. I could use rock wool. I could use virtually anything. What's important here is the water control, the air control, the vapor control, and the thermal control are all on the outside of the structure, and I have a back ventilated and drained cladding. Yay! And I can build this anywhere. I can build this in Montreal, in Miami, in Mojave, Monterey, Minneapolis. I don't have to do any calculation. How do you decide what the thermal resistance should be? Whatever you think it should be, double it and shut up, because I've never gotten it right in all my, So what are you now doing? Well, I'm going to R40, R50 walls. Well, that's insane. Well, not now. It was 30 years ago. That's another policy discussion for later. Well, can I make this almost as good but less expensive? Well, sure. I can replace the concrete structure with steel studs and gypsum sheathing without paper, like something like dense glass gold. Everything else stays the same. So look, all I've done is taken the expensive part out and done this. And notice that I've not insulated the steel studs. Insulating the steel studs is a thermodynamic obscenity. If I take a 6-inch steel stud and I put an R20 bat in it, the effective thermal resistance is 4. I'm losing 75% of the thermal resistance because of the conductivity of the steel. Steel is 300 times more conductive than wood. Now I know this, I've never seen wood wiring. I've never seen a wood frying pan. Well, once. So you put the insulation on the outside. I learned this as a child growing up in Canada. When it got cold, us children would put sweaters over the outside of us. We didn't eat them and shove them into our ribs. You need to be a sweater wearer, not a sweater eater. Now, the only time you insulate steel studs is for acoustics. So you want light, fluffy stuff. So you'd never put spray foam in that, right? Because it'd be like a drum. Now, this is, the most efficient way to suck energy across a building. It's called a steel stud. Whether you insulate this at all in the cavity, you wouldn't be able to tell the difference in the utility bill. But if it was uninsulated and it didn't have fiberglass, you would know right away from acoustics. So you wear the sweater thermally, and you eat the sweater, a fluffy sweater, acoustically. Whoa! Yeah, all we have to do is teach this. How do I attach my cladding to steel studs? Well, you don't want to have continuous steel girts through this because they're conductive. And we call them Z bars in Canada. You call them Z bars. I grew up listening to ZZ Top. I drove a 240Z. All right. So we've actually figured out how to use conductive stuff in a non-conductive way to transmit and control the cladding systems to the metal studs. We know how to do this. We don't do it. We should be doing it. We know how to do it. It's frustrating. With a wood wall, I can fully insulate the cavity. And this is awesome, right? And I can use any insulation I want in the cavity. I can use mineral wool, rock wool, cellulose, fiberglass, Gloria Vanderbilt's ground up blue jeans with borates in them, low density foam, high density foam. On the outside, I can use any insulation I want. What's important is the order. And when I get in cold places, I have to have more of the insulation to the outside than the inside. Well, why is that a big deal? Well, guess what? The Center for Disease Control in Atlanta and the Harvard School of Public Health say, oh, because of this COVID and health stuff, we want 35 to 40% relative humidity year round. A typical wall or roof in a cold climate can't handle it unless you put a lot of the insulation to the outside. Humidification is great for people as long as the humidifier is clean. Otherwise, it's a bioweapon. See, and so the Mayo Clinic says use distilled water and clean it every other day. I see that happening all the time, right? Like this, sure, we're going to distilled water and we're going to clean it. I mean, all the time. And then I'm finding that we don't have enough insulation to be able to do this. We're basically building, we have to build the buildings like art galleries, museums, and indoor swimming pools and auditoriums. We're not doing that. And so I'm telling people, humidify and control the humidity at the health recommended rates for maybe 8 months of the year, and then 4 months of the year, lower the humidity based on the outside temperature. So I'm saying, save the people for 8 months, save the building for 4, or start off with a complete clean sheet of paper and do a high energy efficient structure. And the only people that don't understand this are the health community, right? So if you can't do math or physics, join the Center for Disease Control in Atlanta. I'm sure I'm going to get calls for that one. Rain, all cladding systems leak. This is a very simple test. It's not an ASTM test, so it's practical. ASTM stands for another stupid test method. This person is clearly a Canadian. He's a hoser. And we find that about 10% of the water passes through the brick in about 30 seconds. And it doesn't pass through the brick, it doesn't pass through the mortar, it passes through the joint between the mortar and the brick. So this water needs to be drained back to the exterior. All claddings leak. They all leak. So, the old days we would use tar paper, and the space was 1 inch because of the mason's knuckles and fingers. So we call this a water control layer. We call it now WRB, building wrap, house wrap. I don't care, whatever you. I named it a drainage plane. I got famous for that, but alcohol and a musical were involved. When I was dating my wife to be, as an architect, we were watching My Fair Lady, and in the middle of My Fair Lady, Eliza Doolittle says, "The rain in Spain stays mainly on the plain." I turned to Betsy and said, "We need to drain the rain on the plain." She said, "Where is that blasted rain?" "On the drainage plane." The next day I spoke to the Boston Society of Architects. Drainage plane has made it into the code. Some of that story is true. Anyway, so how much of a gap do I need? Not very much. The whole deal is controlling hydrostatic pressure. If I don't have the water build up, I could live with holes. See, for water to enter, you need water, a hole, and a pressure. And the pressure is hydrostatic pressure. So what are the odds that you're going to put nails and screws to your WRB? So you got holes. I don't care how good you are. But if you drain the water away, it don't matter. So here's a drainage space. How many nail holes do I have in this cedar shake wall? Thousands. Does it leak? No. Why? Because I've drained the water away. I don't need much of a gap. I just need something. So 32nd of an inch DuPont Tyvek drain wrap. This is a 60s technology. It's groovy. So we call this the Rainscreen. I, of course, did some experiments. The guy that really did all his work was his doctoral dissertation, John Professor Straub. It is a unique piece of work done in the 1990s, which is redone of work done half a century earlier, but it was just special stuff. And then I created something called the Beer Screen, which is a joint venture between Budweiser and Dow. So I just wanted, I submitted this for a patent. All right, so where do I go here? What's my advice to you? Well, I like wood frame and I like advanced framing. 2x6 24-inch centers, single studs. And that's my base assembly. And that base assembly, I can insulate with anything that I want. Fiberglass, cellulose, spray foam, low density, high density, I don't care. But it's not good enough. I want to put continuous insulation on the outside. I want to wear a sweater. So I can use EPS, XPS, isocyanurate, mineral wool, stone wool, whatever. I'm usually limited to 1.5 inches in thickness because that's what the cladding companies, the siding companies say I can nail through before having to use a 1x4 as a furring strip. If I have to go to furring strips, I'm going to go with 2 layers of rigid insulation on the outside. Yeah, whoa. So that's, my middle assembly. Well, I don't like that type of insulation system. Well, okay, give me a truss wall and blow it filled with cellulose or fiberglass or whatever. Feel better about yourself? Great. Well, there's too much wood in that. Let me build another wall outside of the other wall and fill it with stuff. Fine, double wall. All of these work. Pick one. All of them work. So this is the one that I'm pushing most of the production home builders simply because I can do advanced framing less expensively than 2x4s, and I can integrate the water control with the extruded polystyrene and some furring strips and cladding. Look, it's not spectacular, but it's pretty darn good. Can I be better? Well, sure. I could, use different insulations. Could I have 2 layers of mineral wool? Absolutely, knock yourself out. Could I have a truss and fill it with cellulose? Yeah, knock yourself out. Can I do a double wall with foam or double wall with fluffy stuff? Yes. We want to go from the Yugo to the Porsche, right? I'm happy just with Lexuses, but we got to do better. And those are a bunch of options, and you'll pick and choose your materials based on what your carbon accounting, your understanding of energy, embodied energy, which, by the way, it's not easy to understand. And I get into trouble when I say if we did our taxes the way we do our carbon accounting, the IRS would lock us up. We got stuff to do, but you need a high performance assembly. With that, Brett, you're on.
Hey, yeah, great. Thanks, Joe. We got a lot of questions coming in. So let's just try to get to some of them. I saw you all put some questions in the chat, but feel free to migrate them over to the Q&A so I don't miss any of them. One of the first ones was, well, actually, let's get to that one a little bit later. But going back to the flavorless popsicles, also known as the icicles, the question was, is this a definitive sign of a poorly insulated roof or just an improper attic assembly?
I'm going to say that we know so much about ice damming. I view it as a poorly designed and insulated roof. I mean, there's no excuse for ice damming.
All right.
I, I, I got a whole bunch of papers on ice damming I wrote up on our website. You know, dam, ice dam, and whatever. Just, you know, there's no excuse for them, right? And the idea of using, electrical heating strips, that we call that an Aspen answer, because they were saying, well, they fly in on their private jets to tell us about climate warming and change, and then they have stupid designs with, yeah, but we have solar panels to generate the electricity to handle the ice dam. Just build the roof right. Come on, folks. Come on. Anyway.
Well, speaking of solar panels, I was thinking about and still trying to think through the comment at the beginning you made about the darker roof versus the white roof, or the reflective roof. I think we can have reflective roofs that aren't necessarily white. And you were just saying the longevity of that roof in regards to a darker roof, you'd have more durability. So first of all, did I hear that right? And then second, how does that same conversation play out when you have solar on the roof?
All right, well, the lighter the color, the longer the life of the roof assembly. There's just no mystery there. Now, folks, when I tell you about solar panels, please don't hate me. I love solar panels, but they need maintenance. The inverters need to be changed. You put them on the darn roof, you have to get at the damn thing to change them. You need accessibility. I mean, I have got a net zero house for our daughter, and we got 8.5 kW, and over a 10-year period, every one of the inverters had to be replaced. I'm still a solar guy, okay? It's just that, oh, well, now I need to be able to easily access them to be able to get at them. They also generate an insane amount of heat, and that heat will age your roof, okay? So you need to ventilate under the panel to save the roofing membrane. Mm-hmm. Then you got like a whole bunch of holes in the damn roof, right, so the panel doesn't blow away. I'm not trying to talk you out of it. I'm simply saying that we've learned how to do this, but we learned from really being dumb. So it's important that when you're going to put solar on your house, don't have Billy, Bob, and Guido do it on their first job. Yet, okay, we know how to do it, but we've not been doing it.
Yeah. So going back, I was trying to understand. I think you were saying the entire roof assembly's longevity was more for the darker roof. Is that correct, or did I hear that right?
Well, yeah, the durability of everything but the membrane, yeah, was greater because of the energy flow. Was all
okay. Yeah.
So it's like, gee, if I make my roof energy inefficient, right, it's going to last longer.
Right.
Well, yeah, but I feel bad about that. That's kind of dumb, isn't it? I mean, I want an ultra energy efficient roof that's going to last a very long time. That means changing the way we build.
Okay.
You can't get your money for nothing and your chicks for free. There's no such thing as a free thermodynamic lunch.
Right. Got it. The next question up here is the smart. What are your just general thoughts on the smart vapor barrier approach? And specific, the question was here to that on the inside of the studs in a cold climate.
Well, if you have the right amount of continuous insulation on the outside, you don't need the smart vapor retarder at all, right? Mm-hmm. So I'm saying that there's no reason for it. I'm sure I'm going to end up with a roll of smart vapor barrier in my bed tomorrow morning when I share this next. That's a Godfather reference. If you're in a cold climate and you have a smart vapor retarder on the inside, that tells me you don't have enough continuous insulation on the outside to make it work, right? I can't see a reason for it. It's also insanely difficult to make airtight. You're better off having. So I'm tired of the double walls with the smart membrane. I would like to have my air control layer on the outside of my inside wall, mm-hmm, plywood or OSB or whatever, then have a whole bunch of insulation to the outside, and a whole bunch of insulation on the inside, and I can dry to the inside and I can dry to the outside. And I'm using a smart wall, not a smart membrane. I just came up with that. That's going to be, I'll get into trouble with the folks out of, well, you know who.
Right.
I know.
Fair enough. Well, can you do a brief description of a good retrofit assembly system? And really just, you talked a lot about the new construction approach and doing it right from the start. Obviously, when it comes to existing, there's so many different things we have to consider. So I guess what can you do to speak to an existing housing approach?
Well, okay. We retrofitted an 1850 farmhouse in a historic district and had everybody hate us at first and then loved us later. But so we basically stripped the cladding off the outside, put on plywood to provide racking resistance, sealed the plywood as our primary air control layer, and then put two 2-inch layers of isocyanurate furring strips and wood siding. And then we blew the cavities with cellulose. So we ended up with an R40 retrofit wall. And the historic people were all mad at us at first because it looked like we were going to change the appearance. What ended up happening is ended up looking exactly the same as it did before we started, because it was real important that, there's a reason why a Prius is such an ugly car. People buy Priuses to show how socially responsible they are, and they want everybody to know we're socially responsible, so the car is ugly. I want people to walk by the house and say, what a beautiful house. They don't need to know that it's ultra efficient. In fact, if I had done my job, nobody knows that I was there. So then we replaced the windows, and the windows were triple glazed Krypton filled. They were Lex Luthor Industries. And our 80 unvented roof, but in our part in Boston, we didn't have to have an overvented roof because I didn't have enough snow to deal with. We had a rubble foundation on the inside, and I did that with R30 straight polyurethane foam and a drainage layer on the inside. All of this is on our website. You can see the step-by-step whatever on how to do that. Was it cheap? No. But I'm in a part of Massachusetts where we spent $450,000 on doing this. The energy payback would be never, but the financial payback was immediate, right? I mean, people say, "My God, I want to buy that house," and so we're going to get we've already got our money back. I want to die in that house, because I love it. I don't want to end up in a nursing home. I'm going to have my own nursing home in this net zero retrofit. So where do you put the solar panels? In the backyard, on a shed. I can get at it to fix it. Put it on that roof. That's I'm going to be old. I'm already old. Hire young people that are going to swing stage and be Spider-Man. No, just put the panels on some place that you can get it to fix them, because they're going to need to be fixed and maintained.
Mm-hmm. Yeah. Another question that came in is, it looks like the vapor control layer is on the exterior of some of those assemblies you were recently showing, XPS, for example, to the exterior. Is that a function of where and I'm not sure of this acronym, but where the DP lies within the wall assembly? Thoughts?
Yeah, the DP stands for dew point.
Dew point. Okay.
I hate that phrase, but what we're doing is that's where the condensing surface is. So the condensing surface is basically the membrane on the outside of the structure, and I need to control the temperature of the condensing surface, so I need a sufficient amount of rigid insulation on the outside so that I don't have to have vapor control on the inside. The building code has a nice table that tells you, based on each climate zone, what ratio of insulation to the outside to the inside you need to stay out of trouble. So if I'm in climate zone 5, I need 30% of the thermal resistance to be in the outside. If I go to climate zone 7, I'm going to need 50%. But here are the weasel words. Okay, I wrote all this. It took 10 years and whatever. We were assuming 35% interior relative humidity during the coldest part of the winter.
Mhm.
You push it to 50, you're going to need to increase by 50% the thermal resistance on the outer layer. All right? So the ratio is going to depend on not just the location, but the interior conditions. And, the people that don't have this figured out are the people who build and design hospitals, museums, and art galleries.
Mhm.
How do I know that? Well, who gives me the call? Joe, the world is coming. Oh, our wall is wet. Well, you freaking ate the sweater. You should have worn the sweater. I actually don't say that. I give them the look, and I'm polite now. And you needed more stuff on the outside, and there you go.
Mhm. Looking at specific insulations, especially the ones that end up on the inside, like in the wood assemblies, what have you seen or thoughts on, potential off-gassing of insulation types, or, you have these trade-offs, right? Maybe it's a little more resistance, better R value, but, in
Well,
regards to embodied carbon or health, right? So,
the biggest risk is obviously spray foams,
hmm,
and they're not a risk if adults put them in. And the trouble is the ratio of the A and the B have to be really, really don't do that. And so if you are sensitive and blah 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 blah, maybe that's a technology you should stay away from. Now, if I was to blow the wall cavity filled with cellulose and not have enough insulation on the outside, and I get water and mold, I can take a green insulation like cellulose and end up creating a health issue because I got it wet. Well, yeah, there's always some kind of risk. So, gee, Joe, how did you decide to do it? Well, we blew the walls with cellulose. We put extruded polystyrene on the outside of sufficient thickness to control the condensing surface. And why did we choose extruded polystyrene? Because I wanted it to be my water control layer. I didn't care about the embodied energy because when I did it, I wasn't on the wavelength. Well, what if I wanted to do this with timber fiber insulation, fiberboard? Well, okay, we can do that. I just need to have drainage behind it as well as in front of it. We now know how to do that. How did we learn that? Well, we watched the Germans screw it up. You're not getting into humor, you see. They were into it first. They made the mistakes first. They figured it out. So we should not invent. We should make new mistakes, not ones that we can avoid. So anyway, and what fiberglass comes with a risk, right? If it gets wet, it smells like somebody pees in your wall, right? You should be careful with everything.
sure. Fair enough. What's your opinion of the innie versus outie window insulation in thick, highly insulated wall assemblies?
Well, all right. The outie works better. The innie looks better.
Hmm.
You might not think that's important, but I've got an 1840 house, and I added all this insulation to the outside, and I'm married to an architect. My daughter is an architect. We have lots of architect friends, and the damn thing had to look nice. So the window was an innie because we didn't have to change the trim on the interior, right? So when you're inside your house, it doesn't look weird. It looks normal. Then we returned the exterior trim to the outside, and it felt good. Now, if I'm doing a modern building and I can have it look with a different style, I'm always pushing the windows to be outies because they perform better out there.
And when you say perform better, you just mean resistance
You're,
to
li- where
heat?
you're lining up the thermal performance of the continuous insulation with the thermal performance of the glazing system, right?
Sure. Yeah. Well, and I'm thinking of some of these different assemblies, and I'm just curious, especially when we've got these massive labor shortages, right? And I'd be curious just what your general thoughts are on the approach of which one's more enticing for someone to take a job, right? Because I think of exterior insulation and I hear all sorts of I don't want to deal with that, right? That's just too much effort. We don't want to do it. So, I mean, how do you factor in what people will actually be willing to do?
Well, it's not really complicated.
Hmm.
Um, Treat your people well,
Hmm.
pay them well, teach them, and they will do it.
Hmm.
I mean, if you're trying to run this like a commodity business, it doesn't work.
Hmm.
Well, all right, I'm going to tell you grandpa stories now that I'm a grandpa. I've been waiting for houses to be built in factories efficiently for a half century. I'm still waiting, right? So, oh, it's faster, it's better, the robots are going to do it. Yeah, 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 yeah. Well, do you really think that the big production builders are that colossally stupid that they're not going to actually adopt a more efficient, practical, better technology? No, we want to be inefficient. We want to spend money. We want to waste money. We want to lower our profit margin and increase our risk. So we're going to do the stupid thing. They're not like that. Just that it's not as easy as people seem to think. Now, ponder this. When you build something off site and you move it on a truck, you're mostly moving air, right? Well, how do we like to ship things? We like to have, we want it all smooshed together, high density from a weight perspective, right?
Hmm.
The shipping is not free. You don't want to ship air. So boxes are not as efficient as panels, right? This is Brett, this is a discussion for another time. Invite me back, maybe, and we can talk about this. I've gone through the wars with panelization and production housing and whatever, and I still like stick built by people who know stuff, right?
Sure.
And I
Well, and yeah,
and I invest, and I would rather invest in people that know stuff than some crazy robot done, by some computer simulation that nobody understands, right?
fair enough. Yeah, and I appreciate you bringing up the prefab and modular, because that does seem to be sort of one of the answers that gets thrown out to uh, a labor issue. So
And,
thanks
and,
for
they, and they keep making money, right?
right.
Well, that's a joke. They keep going out of business, right?
That's
Gee, they keep going out of business. That's because they're such a great idea.
fair enough. I wanted to go back, and I appreciate you bringing up the resiliency aspects in many of these cases in regards to winds and flooding and fire resistance. Now, I was trying to wrap my brain around real quickly what you were talking about in the colder climates with the additional roofing layer for fire. Just to maybe have you reiterate that again. Is that something that somebody actively needs to move during the cold season, moving event, or what did I hear on that? Can you describe that again?
Well, think of an event that remains open all of the time.
Hmm.
And it's real important to remain open in the winter to control ice damming. But when you have a fire, you want the vent to automatically close so you don't get embers.
Okay.
Think of an operational event that's open all of the time except in the event of a fire.
Hmm.
Now, you can do this a couple of ways. You can do it with a motorized vent.
Hmm.
You can do this by G. Most people know that a fire is coming. Let's close the vents.
Hmm.
Or I can put in a mesh that's intermittent, that basically when it gets hot, it goes and seals up.
Hmm.
So there's a bunch of technologies. And the most innovation is happening in the big, expensive custom homes in places like Sun Valley, where you have a lot of snow and fire.
Hmm.
This is great. So let the rich people play and then figure it out and adapt the technology for us normal people.
Sure. And on the note of the unvented attics, as far as the hurricanes go, does that also apply to strong straight line winds, or was that just for
Yeah,
hurricanes?
that's for everything.
Yeah, for all winds.
The,
Yeah.
the wind loads. The guy that knows most about this is uh, David Pravat. He's a professor of engineering at the University of Florida in Gainesville. They have some kind of a semi-professional football team called the Gators.
Hmm.
It's a joke. You see, you people in Michigan think you play football better than the people in Florida. All right, never mind.
Ah,
So
I leave it to the yeah. Fair enough. Well, so one of the final kind of questions that came up is, and you were telling me before we got on here, is you're coming out or updating multiple books for multiple climate zones. It's not just cold weather. So can you just tell us a little bit about that?
well, the I first wrote the stuff in the Moisture Control Handbook in 1989, and we've learned a lot, and rewrote it last year. It's the hardcover, and it's, gee, Joe, it's different. Well, yeah, because I learned a lot. My God. Then in the late 90s, I did the 4 series builder's guides for cold climates and hot, humid, mixed humid, hot, dry. And I just rewrote the cold one built because it was the most difficult to do. It was the most complicated to deal with, and it had the most interest. And so my financial advisor, my wife, basically, the managing partner of the firm, the architect, said, "You're an idiot. Why would you do a hot, dry book? Nobody cares what happens where it's hot and dry. It's boring. Do cold and miserable and disgusting and right away." And so that became second. And then the mixed, humid, and marine, that has the biggest, the most controversial questions that people are asking. I don't think they're controversial at all, but people are confused. It's neither cold, it's neither hot, and it's not dry. Marine is complicated, and if you've ever visited Portland and Seattle, their personalities are strange to begin with, but the climate is unusual.
Fair enough. So where can before we head out, where can people go to learn more about these, learn more about any of the resources they have available, and stay up to date when they come out?
Well, if you go visit buildingscience.com, I've got 200 building science insights. They're available for free. They're not behind a paywall. We got 1,000 papers. Everything is there, and just download it and read it. You're not going to have, obviously, the incredible wit and humor and jokes with those. So if you want some of that, you could. I do a 16-hour building science fundamentals class.
Yeah.
Tuesdays and Thursdays, 2 weeks in a row, from 1 to 5, and all of the stuff I talked about today, I lay it out in more detail. But you don't need to take the class. The PowerPoints are available for free online, and you can download everything, whatever. But some people like to hear the stories, and they learn easier. In terms of the books, we've got the Moisture Control Handbook, which is a hardcover book, the Cold Climate Builder's Guide, which is 500 pages, just came out. Those are the 2 new ones. The others are available, but this is going to sound really bad. Don't share this with my managing partner. Don't buy them. Wait a couple of months till we get them done right, okay?
Fair enough. Well, Joe, I really appreciate your time. Thanks for coming out and hanging out with us today on your trip out there. Have a great rest of your week. Take care, and thank you all for joining us. So
it was an honor and a pleasure, and thanks for inviting me.
Be sure to check out all of our courses available online that you can watch anytime and anywhere to pick up your CEUs. Before you go, make sure to subscribe to us on YouTube to get weekly updates and stay up to date on green building science courses, webinars, and home tours. Thanks again.